Okay, so today we're going to talk about using the idea of partial fractions to be able to integrate certain rational functions that we wouldn't be able to. So if you recall in pre-calculus, you learned how to find partial fractions. And so in that class, you may have thought, well, why do I really care to find partial fractions? And you probably had a legitimate question because in pre-calculus, all you really did was, and if you don't remember what partial fractions were, all you really did is you kind of grabbed a fraction such as this, 2x squared minus x plus 4 over x cubed plus 4x, and you grabbed this and broke it up into multiple fractions. And these multiple fractions, whenever you added them, you obviously got that. So it was kind of we were undoing. So if you think about this, pretty much all the way up until partial fractions, you're always taught, hey, whenever you have multiple fractions, get a common denominator, combine them, and get this. So now what are we doing? We're saying, let's start with this and go backwards. Okay, now why is that to our advantage? We'll kind of get to that in a minute, but if you were just strictly to look at this rational function, and if I were to ask you to integrate this, you might have a tough time integrating this because even if you try to use u substitution, you'd see that this would not work, because if you let the denominator equal to x cubed plus 4x, when you find the derivative of this, it would be impossible to get what's on top. So you could see that these are going to be some problems here that we have to deal with. So what we're going to do now is we're pretty much going to um, grab and I'm just briefly going to talk about what we need to do here um, to kind of break something down to partial fractions. So let's take a look at this. Just let's do a quick review of partial fractions. So the first thing we did is we start off by, first of all, partial fractions may only be applied to proper rational functions. Which, what does that mean? The denominator is has a larger degree than the numerator. So basically, what we notice is the degree. So the degree of the denominator is greater than the degree of numerator. Okay, so that's kind of how we know. If the degree of the numerator is larger than the degree of the denominator, then you could just use long division to break this down. So you may not even need partial fractions. Okay, so once you do that, the next step is, the first step actually is completely factor the denominator. Okay, and so then what are we going to do here? So then we're going to focus on the factor. So here's what we're going to say. If the factor in the denominator is linear and non-repeating, such as, I don't know, let's just focus on something like this. Some number over, let's just focus on this for now, x plus 1, x squared plus 4. So if you look at this factor, and what we're going to do is we're going to look at each factor of the denominator. So I'm going to focus on this. If this is linear non-repeating, now why is this non-repeating? Because I have only one of them. And clearly this is linear because x plus 1 is a line. So um, we would say then the partial fraction for the linear non-repeating factor looks like the following. So if I have number over x plus 1 over x squared plus 4, then just for this part, it's going to be a, which that's going to be the constant we need to find, over x plus 1. Okay? Now, we would say that if the factor is quadratic non-repeating, then the partial fraction for the quadratic non-repeating factor looks like the following. So if I go back, let's say, to this guy, what do we notice? If I go back to that guy, we're going to say that's going to be, so this x plus 1 has been taken care of by that. So let's go up there. It'll be plus. So now I need to take care of the quadratic. And so since this is quadratic, why do I know it's quadratic? Because it's x squared plus 4, right? And I can't factor this any further, right? If I could factor this any further, then it would be linear. But this right there is quadratic, and it's non-repeating because I have only one of them. So that would break up to bx plus c over x squared plus 4. Okay, so what am I basically claiming? Whatever this was before I combined it must have looked like that. So what's my goal now? My goal is to find A, B, and C. Okay, now, what if we have, so let's actually kind of speed this up. If factors are linear repeating, this is how we'd break them up. So I think hopefully this is starting to ring a bell. So I'm kind of going to go through this. So what do we mean if they're linear repeating? So what if I have a number over x squared times x plus 1 cubed, for instance? Now, let's be careful here. People always confuse and they think confuse x squared, and they think that itself is nonlinear. That is in fact linear, because think of it. This is equivalent to thinking of it as x minus 0 squared, which notice how that's x plus 1 cubed. Clearly, you look at the inside and you say, hey, look, that's linear and it's repeating because I have 3 of them. So if you see x squared, then that's equivalent to thinking of it as x minus 0, which this itself is just the line y equals x that goes through the origin, and it's repeating because I have 2 of them. So when do we have the quadratics? It's when we have something like x squared plus 1, for instance, right? Notice how this, I can't call that linear because x squared plus 1 is like a whole entity, and this all together is non-linear. Okay, so basically that's what's happening here for that for this problem. So the way this would break up is what? I would have to take all the possible fractions that x squared could have, which here's what it would be: a over x plus b over x squared. So look, see, if you look at this, what's my common denominator? It's x squared. So you might be thinking, well, why do I care about a over x? Because what I'm doing is I'm listing all the possible fractions I could have where this would be its common denominator. So since this is linear, it's repeating, and I have 2 of them, I have to take into account both powers. So it's like x to the power of 1 and x squared. And if I were to get a common denominator here, that would give me the x squared. And then I'm sure you could guess how the x plus 1 cubed would look, because that would be c over x plus 1 plus d over x plus 1 squared plus e over x plus 1 cubed. And once again, why do I care about x plus 1 squared, and x plus 1 cubed? Is because I'm writing kind of like an exhaustive um, fraction or list of fractions where all of these combined, I'm writing all the possible fractions I could get that would still have a common denominator of x squared times x plus 1 cubed, which notice outside of these guys, there's nothing else that I could really put there which would have a common denominator of x squared times x plus 1 cubed. Okay, so what if the factors, and remember at the end my goal is to find a, b, c, d, and e. If factors are nonlinear repeating, what do we get? We get, like if it's something like this, n x plus 1 squared, and let's say, or sorry, x squared plus 1, and let's just say x plus 1. So what do you notice here? This guy is actually nonlinear, and let's call that squared. So it's x squared plus 1 quantity squared, and this is x plus 1. So this, what is it? It's a combination of nonlinear repeating, and that's just linear non-repeating. How would this break up? Well, the nonlinear repeating, it would be very similar to the linear repeating, except in the numerator, what would it be? It would be ax plus b over x squared plus 1. And remember, I have two of them, right? It would be plus cx plus d over x squared plus 1 quantity squared plus, and then I would take care of this factor, which that's linear non-repeating, which would be e over x plus 1. And then once again, my goal is to find a, b, c, d, and e. And once I do that, then I have my partial fractions. So with that quick review, hopefully that's good enough for you to kind of refresh your memory. Here's what we're going to do. Now let's actually put this and work with this in terms of calculus. So for example 1, we are going to say find the integral dx over x squared minus a squared. Okay, and where a can't equal to 0. Okay, so here's what I notice. The problem is this. What would be the antiderivative of 1 over x squared minus a squared? That we don't know. And see, we can't find the antiderivative of this very easily. So what we're going to do is we're going to need to use partial fractions. So my goal is to grab 1 over x squared minus a squared and write this as a partial fraction. So what's the first thing I need to do? I need to factor the denominator completely. And when we factor the denominator completely, what do we get? We get 1 over x minus a times x plus a. And when I do that, what do I notice? We have actually two factors, and they're both linear, and they're non-repeating. So what I know is that this is going to break up to what? A over x minus a plus b over x plus a. So to be able to find out what capital A and capital B are, now we need to work backwards. So what I'm going to try to do now is we're going to put this back together. And when I put this back together, I want this guy to look exactly like that guy. So the first thing I need to do is get a common denominator. So multiply this guy by x plus a, multiply this guy by x minus a. So what you should already notice is once I do that, my denominators are already matching with the left side. So if they are, I'm kind of going to start ignoring that. Now my goal is to make my numerators match up. So I'm going to start ignoring the denominators. It's not like I'm saying they canceled out. I'm just saying, look, my denominator here, when I put these together, this is already matching up with that. So I just need to work with the numerator. So here's what I'm going to say. I'm going to say 1 equals to, because the 1 is the numerator of this guy. And what would this be? It'll be capital AX plus capital A lowercase a. And then plus, distribute that, it'll be capital BX minus capital B lowercase a. Okay, so with that said, now what we're going to do is we are going to group everything that has x's together. Okay, so 1 equals to ax plus bx, and since they both have an x in common, I'm going to factor an x out, so it'll be a plus b, capital X, and then everything that has a lowercase a I'm going to put together, and I'm going to factor out a lowercase a, which leaves me with what? A minus b times a. So now look, a and b, these are I need to figure out what a and b need to be, where this guy ends up looking like 1. So think of it this way. If I look at the left side of the equation, do I see an x here? And the answer is obviously no. So if you think about it, this a plus b that's tied to this x, what do I want? I want this to go away. How come? Because I have 0x here. So what am I trying to do? I'm trying to get this to match up with that. And by the way, this 0x, I mean, it's 0x. Why is it 0x? Because it's not there, right? So I need that to 0 out. And then what do I notice here? The a minus b here, this has to pretty much equal to 1. Okay, so with that said, what is it that we notice here? And by the way, this is, okay, so what are we going to do here now? We're basically going to say, well, what do I know here? A plus b has to equal to 0, okay? And what do I want? I want this, which is my constant. And how do I, which by the way, what does this mean here? This means that this implies that a has to equal to negative b. Okay, now with that said, now what we need to do is we need to figure out what this needs to be. Now look, this is my constant, and what constant do I want this to equal to? I want it to equal to 1. So in other words, what we already know is what? A is equivalent to negative b. So what I could do is I could come back to this and say, look, I want a minus b times a, or lowercase a, for it to equal to 1. So then what does that mean? Well, we already know that a equals to negative b. So I could come here and replace a with negative b. And if I do that, I get negative b minus b times a equals to 1. So this becomes what? Negative 2b times a equals to 1, which if that's the case, then what does that mean? Lowercase a has to be 1 over negative 2b, okay? Or in other words, if I were to solve for b in terms of a, actually, because we were better off doing that because a is a constant, what does this imply? Actually, it implies that b equals to, let's see how it cross multiply, which would be negative 1 over 2a. Okay, so there you have it. So what do we know here? If b is negative 1 over 2a, then what must a be? A, coming back here, a must equal to 1 over 2a. Okay, so with that said, once we have all of this, what is this going to happen? So I could go back now and substitute. So our partial fraction, which is this guy right here, what does that break up to? 1 over x minus a times x plus a is going to break up to 1 over 2a over x minus a plus negative 1 over 2a over x plus a. Okay, now remember the 1 over 2a and the negative 1 over 2a, those are constants, so we're not concerned about this. So here's what we're going to say. The integral of 1 over x minus a times x plus a dx is the same thing as what? The integral of 1 over 2a over x minus a plus negative 1 over 2a over x plus a dx. Now look at how nice this is. See, the antiderivative of this, or let's make it even clearer, this is the same thing as what? I could break up this integral and I could pull the 1 over 2a out front. So it'll be 1 over 2a times 1 over x minus a dx plus negative 1 over 2a integral of 1 over x plus a dx. Now, if you look at this, you'll see why partial fractions are preferred, because what would the antiderivative of 1 over x minus a be? And you should know by now that this is natural log. So this would be 1 over 2a natural log of x minus a minus 1 over 2a. And what's the antiderivative of 1 over x plus a, it'll be the natural log of absolute value of x plus a plus c. Now, you could try to simplify this further because it's ln minus ln. You could write this as a fraction, but we would stop there. Now, why was partial fraction to our advantage? Because we had a fraction here that I couldn't find the antiderivative of, but I used partial fractions, and the partial fraction allowed me to find the antiderivative of that guy. Okay, so let's do one more example, and then I think we can pretty much uh, let you guys discover the rest of this section on your own. Okay, so let me give you one where we'll evaluate, which becomes the following. We could say evaluate the integral of 10 over x minus 1 x squared plus 9 dx. So right away, what do you notice? Just by looking at this, you're like, okay, look, I can't find this antiderivative because it's a little complicated. So we're better off using partial fractions. So if it's 10 over x minus 1, x squared plus 9, the good news is this is already completely factored for us. So what do I notice? The first factor is what? Linear non-repeating. So that's going to break up as a over x minus 1. And then what's the second factor? It's nonlinear non-repeating, so that's going to break up as bx plus c over x squared plus 9. So now that I broke it up, now what am I going to do to figure out what a, b, and c need to be? I'm going to put them back together and get a common denominator. So this guy is missing an x squared plus 9, x squared plus 9. This guy's missing an x minus 1, x minus 1. So once again, my denominators are matching up with that denominator, which then I'm going to focus on the numerators. So what do I want? I want this right side, which if I were to distribute, which is ax squared plus 9a plus bx squared minus bx plus cx minus c. I want all of this to equal to 10. So once again, now I'm going to start grouping all the like variables, so the x squareds. So what does this become? 10 equals to a plus b x squared. And then how about my x's? It'll be plus negative b plus c times x. And then my constants are what? 9a minus c. So it'll be plus 9a minus c. So now here's where I start comparing. Do I have an x squared on the left side? Obviously I don't. So what does that mean? I want a plus b to equal to 0, which what does that imply? A equals to negative b. And then what else do I know? I want negative b plus c to equal, well, this x, notice how I don't have any x's on the left side. So I want negative b plus c to also be 0 because I don't want any x's. So what does that mean? That means that c equals to b. Okay, and so once I have this information, we can now go ahead and solve for 9a minus c, because what's 9a minus c have to equal to? That has to equal to 10. Okay, so using this information, what do I know here? C equals to b. So what does that mean? If c equals to b, I could replace that with b, but we could even do better than that, because if I replace this with b, this will become a negative b, or in other words, what could I say here? If c is b and negative b is a, then what that means here is what? This implies that negative c is equal to a, right? If I multiply both sides by negative, then I have negative b here, and I could replace negative b with a. So why do I like this? Because now I could come back here and say, look, this minus c, I'm going to change it to a. So this is going to be what? 9a plus a equals to 10, which means 10a equals to 10, which means a equals to 1. And once I found a, the rest should fall into place. Because look, if a equals to 1, then what do I know? A is negative b. So, or in other words, b is negative a, right? So then b would be -1. And if b is -1, c is the same thing as b. So then that means c is -1. So now that I found a, b, and c, I could come back and replace that here. So what do I get here? Let me write that down. So we get the integral of 10 over x minus 1 times x squared plus 9 dx. That'll be the same thing as the integral of, what do we have? We had a over x minus 1, and we said a is 1. So it'll be 1 over x minus 1, which notice right away we could find the antiderivative of that, which that's great news. Plus, then bx plus c. And what do we say? B is -1, so it'll be -x, -1x, plus c is also, we said c is -1. So it'll be actually, let's call it -1 over, that will be x squared plus 9 dx. Okay, so now that we have this, I want to break this up. So here's what I could do. I could say this is equivalent to what? 1 over x minus 1. And then I could factor out a minus here from this because they both have a negative. It'll be or let's not forget the dx, minus the integral of x plus 1 over x squared plus 9 dx. Now look, this right here looks like we're kind of stuck, but we're actually not, because here's what we know. This becomes the integral of 1 over x minus 1 dx. X plus 1 over x squared plus 9, I could rewrite that as what? X over x squared plus 9 plus 1 over x squared plus 9. Okay? So here's what we have. So this will break up to negative parentheses x over x squared plus 9 dx plus the integral of 1 over x squared plus 9 dx. Okay, now look. Here's what we know. We know that what? The integral of, so this we should be able to find, because what do we know? We know that the integral of 1 over x squared plus a squared is what? That's tangent inverse of, well, let's be careful. We know that 1 over x squared plus 1 is tangent inverse of x, so this one would be tangent inverse of x over a plus c times 1 over a. Now, where is this 1 over a coming from? Just keep in mind because of the chain rule here. Okay, so let me kind of validate this some more. Why is this the way it is? Because think of it this way. We learned that what? The integral of 1 over x squared plus 1 is tangent inverse of x, right? So basically what we have here is, now we could say, if I have integral of 1 over x squared plus a squared integral, what could I do here? I could factor out a 1 over a squared. And if I factor out a 1 over a squared, what does that become? It becomes integral of 1 over x squared over a squared plus 1 dx. And what do we notice here? X squared over a squared is the same thing as x over a squared. So then what do we notice? We would say, look, this will be 1 over a squared. Actually, I'm running out of space. Integral of 1 over x over a squared plus 1 dx. So this, the antiderivative of this would be tangent inverse of x over a. But now be careful, because what happens here, I would have to consider the chain rule. So what's the derivative of x over a? It's 1 over a. So I'd also have to have an extra a here. Now with this 1 over a squared that was there to begin with, one of the a's will cancel out, which will be plus c. So there you have it, which basically is what that is. So this one we could find the antiderivative of. This guy will use u sub, and then this guy we already could find the antiderivative of. So to use u sub to find that, we would say what? Let u equal to x squared plus 9. Du will be 2x dx. And then what does that mean? 1/2 du is equal to x dx. So let's just grab this whole thing and rewrite it down here, which what would that be? The integral of 1 over x minus 1 dx minus the integral of, we're using u sub, so this there'll be 1/2 here, 1 over u du plus integral of 1 over x squared plus 9 dx. Okay, now we're ready to find the antiderivative of this, which, what's the antiderivative of 1 over x minus 1? ln of absolute value of x minus 1 minus the antiderivative of 1 over u will be 1/2 ln of absolute value of u plus the antiderivative of this would just be what? It would be, think of this as what? 9 is the same thing as 3 squared. So remember, it had to be in the form of a squared. So a here is 3. So this would be 1 over 3 tangent inverse of x over 3 plus c. Just make sure to plug back in for u whatever we called x squared plus 9. So this becomes ln of absolute value of x minus 1 minus 1/2 ln of absolute value of x squared plus 9 minus 1/3 tangent inverse of x over 3 plus c. Now this minus and this minus came from me distributing that negative. Okay, so you might want to watch this kind of the last two examples over again, but notice how without partial fractions I wouldn't be able to do this. It's partial fractions that help me get through all of this. Okay, so that basically takes care of this section. Make sure to ask me any questions if you have any tomorrow.